Hello class, this is Mrs. Ayodeji with today's video on section 10.4, the error in Taylor approximations. As you're watching the video, please write down important vocabulary, formulas, equations, examples, and graphs. Feel free to pause or rewind the video as often as you need so you can get a clear understanding of what is occurring in the video. At the conclusion of watching the video, write down a brief summary of what occurred in the video and submit that summary via the online WISC as well as a top question. All right, let's begin. We've been talking about Taylor approximations, and today we're going to be focusing on how accurate a Taylor approximation is of the actual function value for specific n. And if you recall, we're talking about, for specific x. So what we're going to do is we're going to define a term for e sub n, which represents the error in an nth degree Taylor approximation. So basically, e sub n for x value can be computed by the difference between the actual true function value and the Taylor polynomial function value. And of course, we don't really care about the sign of the error. We're just going to consider the positive, the absolute value version of it. And so we really are looking for an idea for how high the error can go. And we really want to make sure that when we talk about an error, there's some type of limit that we can say. And we call that limit like the bound, not an actual true limit, but a bound. The error will never be above this much. And that's what we are concerned about. And there is a mathematician who came up with a way to bound the error on a Taylor polynomial approximation. And his name is Lagrange, and we call it the Lagrange error bound. And it looks something like this, which basically says that to find the error bound, the error will never go above a particular value. And this particular value can be found by doing this calculation. Okay? Well, we know what n and x represent for an nth degree Taylor polynomial centered about a. But what does m represent? Well, we'll get to that. The thing that we should know is that m represents a bound of the function value. N plus 1, the n plus 1 derivative of the function value on an interval between a and x. So if you recall, we talked about the notation. It's usually Roman numerals to represent the derivative, but sometimes they use the expression. So this really means the n plus 1 derivative of the function is a number that is less than or equal to m. That's where the m comes from. And it doesn't just have to be one particular m, but we'll get to that. So let's explain why this works. So first, let's consider an nth degree Taylor polynomial of f of x about a equals 0. And one of the things we know about Taylor polynomials evaluate at the value of x equals a, or in this case x equals 0, is that the Taylor polynomial and the function value are exactly matching for that a value. In other words, the errors on each of those terms for the function value, the derivative, and any other derivatives are always going to be 0 because the function value exactly matches, the Taylor polynomial value exactly matches the function value when you evaluate both of them at x equals a, in this case 0. Okay, and since we have an nth degree Taylor polynomial, then that means the n plus 1 degree of the derivative, the n plus 1 derivative of the Taylor polynomial is going to be 0, and so in that case we have this that holds. All right, fine. So suppose I have that the n plus 1 derivative of f at x is bounded by some constant n for all x values close to 0. In this case, our a. So in other words, the n plus 1 derivative evaluated at x can be no bigger than some m value, or no smaller than some negative m value, okay? Then we have this holds. This is basically what we're supposing, okay? And d represents how far x can be from a, or the distance or whatever, okay? Well, if I were to evaluate, since at the nth plus 1 derivative of f is exactly equal to the n plus 1 derivative of our error function, we have the same thing right here, and that's from up here. And if I were to integrate both sides, with respect to t, I mean each component with respect to t, I ended up with something that looks like this because m is a constant. Okay, and then I decrease, of course, this is the nth plus 1 derivative, so the integration of it will produce the nth derivative. Okay, and let me go ahead and take another integral of it, and now since this is a linear term, then we're going to have a quadratic term now for our involving our m's. Okay, and then we reduce the derivative power of e by 1 as well, so we get e to the n minus 1. And we keep on doing that, and we keep on doing that. And for any of the, let's say, nth derivative, we're going to have something that looks like this till we get down to n, all the way down to the very first one, not n, sorry. And we get down to something like this, okay? Which makes sense, and this is the factorial, because every time we take the integration of it, we increase this and then divide it by the whatever, you know what I'm saying. So we end up with something that looks like this. And if we convert it to the absolute value, this is essentially the same thing as what we talked about earlier with the Lagrange. This is the Lagrange error bound for that, okay? So now, if I want to use the Lagrange error bound to find the error, how can we go about doing that? Well, really, in order to do that, you need to find an m that is the maximum function value of the nth plus 1 derivative on an interval close to a. And it can be any value that's sufficiently large enough. So let's give an example. So here we have an example. We have a function e to the x, and we want to find e sub 4, which is the error bound of the 4th degree Taylor polynomial of e to the x about 0. And they've given us a small range of x values that we can include around 0. Okay, so again, like I said, in order to do this, we need to find out what m is. And again, it doesn't have to, there's not just one m. There can be a bunch of different m's, but we need to specify the m that we're going to be using. So in order to do that, we need to find out what is the 5th derivative of f going to be looking like, because we have e to the 4, so we need an n plus 1, so for the 5th derivative of our function going to look like? Well, since e to the x is our function, we know that the derivatives of every e to the x is e to the x. So what is the 5th derivative of e to the x going to look like when x is between negative 0.5 and 0.5? And so that means we pick a value that's the maximum, which is e to the 0.5, since that's the highest our x value can be, because e to the x is increasing function. So in this case, we're picking the square root of e as our value for our m. So since square root of e is less than 2, we can let m be any number bigger than square root of e. So we're going to let m be equal to 2, or any other value that's larger than the square root of e. And then we can say that e sub 4 can be found by, it's bounded by, and using the same formula, instead of m, we use 2, and n plus 1 is 5. Factorial and x minus 0 to the 5th power. And that is what our error bound is for our 4th degree Taylor polynomial approximation of e to the x, as long as x is in between this error range. Okay, so that's what how we use it. Now the question is, and then that will be to determine how much our error is. Okay, all right, simple enough. The next part is, how do we know that the Taylor series converges for functions? Well, in order to determine that, we need to look at the error and see what's happening to the error for any Taylor series approximation. Okay, Taylor polynomial or Taylor series approximation. So let's take a look at cosine of x. If you recall a graph like that when we first started talking about Taylor polynomials, as we increase the degree of the Taylor polynomial, we're going to get a more accuracy of the Taylor approximation around larger values of x. So let's take a look at cosine of pi over 2. If I were to use a Taylor series approximation of this, we know that cosine of pi over 2 is equal to 0, but when I compute the 2nd degree Taylor approximation, 4th degree, 6th degree, eighth degree, I don't get to really 0 until around the eighth degree Taylor polynomial. Let's see what happens as we consider cosine of pi. We know cosine of pi is equal to -1. But then let's take a look at what's happening to these values. And as you can see, sorry, let me scroll this down. We're not going to get to -1 till about the 14th degree Taylor polynomial, which lets us know that even though it will eventually converge, it converges to pi/2 function value quicker than it converges to the pi function value. And that makes sense since pi/2 is closer to the point that we're centering the Taylor approximation around. Okay, so again, it will converge just very slowly. So to show that the Taylor series for cosine of x converges to cosine of x, we can show that using the error bound that we talked about. If you remember, this is what the error bound can be calculated at, and this is a Taylor polynomial of nth degree, so it's like partial sum. Okay, and if we just add p to the x to both sides, we get the cosine of x can be equal to the Taylor polynomial plus e to the x. Okay, so in order to determine whether or not the Taylor polynomial will converge to cosine of x, we need to see what happens as n goes to infinity. What happens to e sub n? Will e sub n remain a value greater than 0, or will it get closer and closer to 0? So that's what we're trying to consider here. So by the Lagrange error bound, we know that m is equal to 1. Remember, we talked about m is found by the n+1 derivative of the function, and since the function is cosine and its derivatives are either sine and the derivatives of that are cosine, sine, and cosine, they're greater than or equal, which are less than or equal to 1, then any m value bigger than 1 is sufficient. So we're going to let m equal 1. Okay, and so we have this based off our Lagrange error bound, and this is what we use to define that. That's our error bound for every n. Now we're going to use a ratio test to see what happens to this sequence. Is it going to converge? I mean, this series, is it going to converge? So we use a ratio test, and we end up with this ratio. And we know that x is going to be fixed, and n+2, as n goes to infinity, is going to be getting bigger and bigger. So that means that at some point, n+2 is going to be twice the size or greater of our x. So let that point be big N. So that means every big N value after big N is going to produce a function value that is less than the previous, a sequence value that was less than the previous sequence value. So in essence, this term is going to be going to 0 as n goes to 0 after n reaches some capital N. Okay? And since that's the case, then we know that the error term is going to go to 0, since we've shown that this goes to 0. And that's about it. Oh, also in the book, if you ever want to show that for the sine function and the other functions in our foldable that we said are exactly the Taylor approximation, this is a good tip to have. As n goes to infinity, x to the n over n factorial goes to 0. And we did that before in a previous class. Okay, that's it. Bye.